Hello, my name is Mark Andre, and the topic of our seminar today is going to be fitting GP lenses and their positive impact on patient outcomes and satisfaction. I'm an associate professor of optometry at Pacific University, and we definitely want to thank our sponsor in this project, which is Valley Contact Lenses, which is providing me the opportunity to give you what I think is going to be a very valuable lesson on the basic fitting of rigid gas permeable lenses. Let's start with why we should consider these types of lenses for our patients. Well, I think all of the literature has pointed to the fact that we run into complications with all types of lenses, but certainly they're limited when we look at those patients wearing daily wear GP lenses. Probably by far the healthiest options that our patients have, so we certainly have to consider health at the top of the list as an option to fit our patients in gas permeable rigid lenses. Visual acuity, I don't think there's any question that it's very difficult to compare visual acuities when we look at other types of contact lens forms of correcting patients with contact lenses. Rigid lenses provide outstanding visual acuity. Ease of handling, again, there's no one that'll deny that a rigid lens is probably the easiest lens to handle, especially the corneal GP lenses when compared to other forms of contact lenses. Cost of maintenance, when you look at the solution costs and the overall care of replacing soft lenses, we certainly have to consider the long-term costs, and I would say that the cost of maintenance, the nod again goes to GP lenses. So we've got a long list here of reasons why GP lenses should be considered. And one that's often left off that list is comfort. When studies are done that look at comfort beyond 2 weeks, rigid lenses play out very nicely. In fact, in a lot of cases, patients feel like they're more comfortable in lenses that they've worn. But again, there's an adaptation period there of anywhere from a few days to a few weeks. And the patient needs to be informed of all the benefits of rigid lenses to kind of get them past that initial feeling of a rigid lens in their eye. Because there's no doubt the initial comfort does go to a soft lens, but when we look at long-term comfort and the benefits that rigid lenses bring to our patients, we certainly have to consider them as a viable option for our patients. Now, what properties do we need to consider before we start our lens design? Put together a list here, starting with material, and over the years, with several manufacturers making lens materials, there are a tremendous amount of options that range from DK values that are very low, 0 being PMMA lenses, to extremely high, 150 DK or higher. So there's a very large laundry list of material options available. And if you're not certain as to what would be best for your patient, I highly recommend that you talk to the consultants at Valley Contax or the lab to just kind of get a feel for what they feel would be best for your particular patient. Lens diameter, one of the first things I look at is how big does the lens need to be. The optical zone diameter, probably the most overlooked property of a gas permeable lens, and that is such an important part of the fit of a rigid contact lens, and I'll get into that as I talk about the basic fitting principles. The base curve radius, the peripheral curves, the lens thickness, again, a very important part of a rigid contact lens in terms of how it fits and the mass of the lens and how it stays centered is the lens thickness. And then finally, the power of the contact lens. And I'll get into all of these factors as we go along. Now, one of the things I like to do working with the lab, and again, in this case it's Valley Contact Lenses, is create a lens design that when I call them up, there's a lot of standard features to it, and I don't have to get into a lot of the details about what intermediate curve or peripheral curve or eccentricity value I want, how thick I want the lens. I basically designate the proprietary design, and the most common design that I work with is the C.A.D. design lens from Valley Contax. The proprietary material is Paragon HDS or Paragon Thin. And the reason for that is that lens material can be cut to a very thin standard. The ANSI standards allow us to cut that lens thin and still maintain a nice balance of stability and wettability. And again, that really is going to factor into how well that lens centers on the eye. So we want the lens as thin as we possibly can make it. I want it to be lenticulated, that is to have a carrier that limits the mass of the lens, which is predetermined in the design. And then finally, we've kind of set a standard of 3 diameters, a 9.5, a 9.0, and an 8.5 millimeter lens size as the diameters. Those of you that have been around for a while and have worked in the past with the old Polycon and Polycon 2 designs, you might recognize these diameters. It's not an accident, that we chose these 3. This covers the overwhelming majority of patients that come in for lenses, although sometimes we need to go smaller and sometimes we need to go larger. The vast majority of patients are going to be managed in probably the 9.5 millimeter and the 9.0 millimeter lens. And then finally, the peripheral curves and the edge are very specifically designed for the diameter and power and base curve of that lens. So in lieu of having to tell the lab every single time we call in an order what we want very specifically, by just designating that we want a C.A.D lens and the material, we get all of those things as standard features in the lens. So what that allows us to do is it allows us to concentrate on our decision making down to these 3 variables. And as I mentioned earlier, we always start with diameter first, and that may be counterintuitive to how a lot of you that are listening to this were trained, because I initially was trained to look at base curve first. But I think if you follow along with me, you'll see the value in choosing a lens diameter that matches up with the diameter of the patient's cornea, and then off of that we'll determine our base curve, and then finally the power of the contact lens. The contact lens diameter should be between 2 and 2.5 millimeters smaller than the visible iris diameter. Now, this gets tricky because measuring visible iris diameter is not easy without some very specific equipment. And maybe the best way to tell if you don't have this equipment is to actually put a diagnostic lens on the eye and just kind of eyeball it and see how it appears in terms of size in relationship to the cornea. But what you're looking at here on the screen are 2 forms of measuring visible iris diameter. The first one is a reticule, an eyepiece reticule that slips into the slit lamp. So one eyepiece comes out, you slide this reticule eyepiece in, and it allows you to measure within at least 0.2 millimeter accuracy the visible iris diameter. On the right, what you see is a biometric ruler that is one of the tools that comes in the Medmont topographer. So for those of you that have access to a topographer, you may have a tool like this in the software that allows you to place the plus marks at 2 points, and then it automatically draws in a line and determines for you in millimeters what the diameter of that is. Now you'll probably say that's not going across the horizontal meridian. In this particular case, this cornea is so large that it doesn't entirely fit on the screen, so we have to use what we call a diagonal visible iris diameter measurement, which is kind of a nice average between the horizontal and visible iris diameter measurements. Now, we've studied this for years, decades now, and looking at diameters of corneas, and it's going to range, the range is going to vary from one region of the country to the other. But in the Portland, Oregon area where we're from, you can see here a chart of 200 consecutive patients that came in and how their horizontal visible iris diameters played out. The smallest being 10.2 millimeters, the largest being 13 millimeters, and the bulk of those falling in the range between 11.2 and 12.4, with an average HVID of 11.8. Now we've repeated this study probably 3 or 4 different times now, and we continually come up, at least in our area, with an average HVID of about 11.8, and as you can see, a nice even distribution of corneal sizes and shapes. For the purpose of good science, let's look at the endpoints here, and it'll kind of demonstrate to you the importance of contact lens diameter. If we look at the very smallest eye in this 200 patient sample at 10.2 millimeters, and the very largest eye at 13.0 millimeters, and if we were fitting everybody with the exact same size contact lens, I think you'd appreciate that the 9.5 millimeter lens would look extremely large on the 10.2 eye, and it would look fairly small on the 13 millimeter eye. So for this example, it just kind of gives you an idea of how important it is to look at the diameter of the contact lens first. And in reality, on the 10.2 millimeter cornea, we're probably going to be looking at the very largest an 8.5 lens, and as you can see, I kind of superimpose what an 8.2 millimeter lens would look like on that eye. And on the 13 millimeter cornea, at the very largest, we'd probably look at a 10.5 millimeter lens, which is going to allow for a much larger optical zone, for that to take into account if we were to do reverse ray tracing, that there's much more light entering in this eye, so we want to provide this patient with more optics. We want to eliminate glares and halos that come from a smaller optical zone, especially when the patient's eye is dilated at night and in dim lit situations. So we're probably going to be looking at a diameter around 10.5 millimeters. So in both of these scenarios, our kind of off the rack diameters of 9 and 9.5 may not be adequate, but keep in mind that these are the very, very endpoints of this study. Now when we look at diagonal visible iris diameter, and here's an example of one of our patients with a fairly flat cornea. You can see K readings in the 42 diopter range, and typically with flat eyes we tend to find that they're a little bit larger. So in this particular case, we're looking at a fairly large eye here, and it just gives you a good example of how we're measuring these corneas to get an idea of where we're going to start on the fitting. Again, what we find is that the majority of these corneal diameters are in the 11.2 to 12.2 or 12.4 range, and in this particular class, this is our class from 2012. You can see that the overwhelming majority of these eyes, if we were going to fit them in a rigid lens, would be able to be managed with the 9.5 and 9.0 diameter. So with just a simple set of a diagnostic set of 2 diameters, you're going to be able to fit in the overwhelming majority of these particular patients. And in this study, as you see, the average HVID, in this case it was a diagonal visible iris diameter, was 11.77 millimeters, very close to that 11.8 that we come up with in pretty much every study that we've done on corneal diameters or visible iris diameter. Once we determine the diameter of the contact lens, we're then ready to determine the base curve. And we've determined that there's really 3 rules that need to be maintained for long-term success of rigid lenses. They're very simple rules. Let's walk through them one at a time. The first one is that the contact lens should clear the center of the cornea. If the contact lens is coming in contact with the center of the cornea, the lens acts very much like a teeter-totter, and with the cornea being the base, the lens will rock from side to side, and it's nearly impossible to center the lens properly. So very first thing we want to do is make sure we've cleared the central cornea. Now ideally what we've determined is that we want about 10 to 20 microns of clearance, and in this particular case the simulated Fluorescein pattern shows us just under 20 microns of clearance. Once we get over 40 microns of clearance, we're looking at the possibility of forming air bubbles. Definitely too much tear film trapped underneath the lens tends to lead to lens flexure, and just creates a situation where we're using a lot of the tear film to determine the power of our system, and we really want to limit that again to between 10 and 20 microns of clearance. We can design a lens using the topographer, and for a good teaching example here, we've got a patient with a 42 by 44 diopters of width of rule astigmatism. We're going to design 2 lenses. We're going to design one that's flatter than K, and in this example 41 diopters, which is a diopter flatter than the flat K of 42 diopters. And we're going to design a lens that's on flat K, 42 diopter lens, both of them 9.5 diameters, and you're going to get an opportunity to see exactly how these lenses look on eye when we go, flatter than K and design a lens that's on K.